All right, so this is the last video and the last topic that you're going to learn this year, and it's going to be section unit 7C, and it's our Pythagorean theorem. This is something you all will be using next year in geometry. So some of the other videos that we've learned you will use in geometry as well, but for those of you going to Algebra 2, 100% you're going to be using those, but every single one of you will be using this next year and quite frequently throughout the rest of your high school. But what you'll know is students will know how to solve for the side of a triangle using Pythagorean theorem. All right, so let's go ahead and talk about Pythagorean theorem. All right, so Pythagorean theorem can only be used when we're dealing with right triangles. If it's not a right triangle, then we can't use it. And we know that this is a right triangle because of this little square in the corner, and it's telling me it's 90 degrees. So if it's not 90 degrees or not a right triangle, we cannot use Pythagorean theorem to solve for this. You'll see that you can use Pythagorean theorem to classify later on, like if it's an obtuse or acute. But if we're trying to solve for the missing side length of something, using Pythagorean theorem, it must be a right triangle. All right, now there's certain parts of the triangle that you have to know what they are, and that is here. The side opposite of our 90-degree angle is referred to as our hypotenuse. All right, and then the two sides that create that 90-degree angle, that come together to form that 90-degree angle, they're referred to as our legs. And when we're dealing with Pythagorean theorem, the hypotenuse will 99% of the time will be referred to as the letter C, and then the legs will be referred to as A or B. And it doesn't matter which one you label A or B, they're interchangeable, but it's just your legs will be referred to as A or B, and your hypotenuse will refer to C. And now there's a formula, and the Pythagorean formula, let's say theorem, is going to be A squared plus B squared is equal to C squared. And one of the things I want you to understand with this is because all I see here is a triangle, right? Well, what this is actually telling us is and I'm going to play a video for you in just a second about this, is when we deal with A squared, we learned something before about a formula of a side squared, and that's actually the formula of a square saying the area of a square. So when we're actually solving what this Pythagorean theorem is, it's actually telling us that the area behind these two legs, the square, that if we were to extend those and draw those out, that square is actually, when we add the area of the two legs, is actually the same as the area behind the hypotenuse. So it's actually referring to the area back here and telling us that the area behind the sides of the triangle is what we're adding and setting equal. And then when we solve for it, we can then, by taking the square root, we can figure out, well, what would that side length have been? So I'm going to play a little video for you that shows this visually, that we're actually dealing with the area behind those triangles. And then we're going to go ahead and just solve some problems using this Pythagorean theorem. All right, so as I was saying to you before, that with our Pythagorean theorem, what this is actually saying is that the area behind the sides of the triangle, that when we add the area behind the two legs, that it will equal the area of a square. So as I was 3, 2, 1. So as I was explaining before, when we're actually dealing with Pythagorean theorem, although all we're seeing is the shape of a triangle there and the side lengths of the triangle, when we see A squared, B squared, and C squared, well, we have learned before that the area of a square is the side squared. So what that is actually representing is that the area behind the legs of the triangle, when we add those two areas together, as I was saying, it is the area of the square behind the hypotenuse. And this video here will show you that by using the liquid here, but it's showing that it's covering the area of these two squares, and you see it's forming this triangle here. And you'll see that the liquid in these two squares is going to fill up the liquid of this here. So when we're dealing with the Pythagorean theorem, even though we only see a triangle and the sides of the triangle, it's actually telling us that the area of the squares behind the legs, when we add them together, it's equal to the area of the square behind the hypotenuse. And you can see that here. So you see as it turns, it's now filling up from the smaller squares to that larger square, and you see we have our triangle that is here. So we can see that when we're actually dealing with this Pythagorean theorem, although we use it for the side lengths, it's actually telling us that the area behind the shapes is what is actually equal. All right, so what we can use a Pythagorean theorem for is in a right triangle, we're able to solve for the missing side length of one of the sides of the right triangle. So as long as if we have two of the three side lengths, we can solve for that missing side length using this formula for Pythagorean theorem, which is a squared plus b squared is equal to c squared. And as we talked about, the only letter that really truly matters that we make sure that we have to put in the right spot or needs to be C is our hypotenuse. And that hypotenuse is a side opposite of the 90-degree angle. So this side that is opposite 90-degree angle always must be C, as we talked about. The other ones could be interchangeable, where this could be A or this could be A, or we could refer to this one as B and this one as B. It doesn't really matter because the A and B just are referring to our legs. But it's important, or the only one that actually truly matters is our C must be our hypotenuse. So when we're solving for this, what we'll just do first is let's just go ahead and identify, well, let's just say our A is equal to 3 because we're just going to say it's this leg. So that means the other leg must be our B. So B is equal to 4 and C is then equal to X. So I'm just going to go ahead and substitute these in. So we have 3 squared plus 4 squared is equal to X squared. And now once we go ahead and identify our legs and our hypotenuse, and we plug it into our formula, we are just simply just solving like we would any other equation. So to do this, first we must square the number. So we have 9 plus 16 is equal to x squared, and 9 plus 16 is equal to 25. So we have x squared is equal to 25. And as we talked about before in our previous unit, if I'm taking the square root of a number, let's say the square root of 4, well, we know that we can rewrite 4 as 2 squared. And anytime our index, which when nothing's written here is understood to be 2, matches our power, we know that they will cancel each other out. And our number on the inside is our answer too. Or we're asking ourselves here, what number squared is equal to 25? But we know that in order to solve for this, we talked about our inverse operation of an x squared being the square root. So they will then cancel each other out. And now x is equal to the square root of 25, which is equal to 5. So it means that this side length must be equal to 5. Now, the one thing that I just want to talk about briefly, for us right now, it's not really something I'm going to look for. But if I was your teacher in geometry next year, I always made sure that my students showed me the correct algebraic work. So, but for now, we're just kind of going through this topic just briefly. But when we have this x squared is equal to 25, so we're asking ourselves, what number squared is equal to 25? Well, this actually generates two answers because 5 squared is equal to 25 and negative 5 squared is also equal to a positive 25. So when we're actually answering this, the correct way of doing this algebraically is when we have a number squared is equal to 25 or whatever it may be, and we're getting the answer, it actually generates a plus or minus answer. And then since we're dealing with the side length of a triangle, and we know that when we deal with length and distance, it must be positive, we will then reject the negative as an answer and just say that x is equal to a positive 5. Now, that's the way I made my students do it in the past. Whether or not your teacher doesn't make you show that plus or minus because we know in geometry we can't have a negative side length, I just want you to see that and then know that algebraically this actually answers or gives us two different answers, a plus or minus. And I never wanted my students getting building bad habits of not remembering that it gives two answers. So I always made them write plus or minus and then cross out that minus just so that we practice good habits. But for the rest of this time, I'm not going to make you do this plus or minus for now because we're just kind of just like briefly learning it. All right, so now the next type of question that we can have is that we could be given what our hypotenuse is actually equal to, and now we just need to solve for one of our legs. And the same thing, it doesn't really matter which one we denote A or B. I'm just going to say A is equal to 8, but we can make x equal to 8 or x equal to A if we wanted to as well. And B is going to be x, and now C must be 10. It's the only one that has to be like a specific letter because it is our hypotenuse. So now we'll substitute it in. We have 8 squared plus x squared is equal to 10 squared. And now we just go ahead and solve. So we will first square this. So 64 plus x squared is equal to 100. And now we just solve it like we normally would by isolating our x. So we'll subtract 64 from both sides. And now we get x squared is equal to 36. And then we will take the square root of each side so we can undo that square and use our inverse operations. X is equal to, I will write it though, plus or minus 6 because remember, a positive 6 squared is 36, and so is a negative. And let's just practice good habits, actually. So we'll cross out that negative 6 and just say that x is equal to 6. All right, there's one more example we're going to do to show you kind of where simplifying radicals actually is something that you'll do a lot when you're dealing with Pythagorean theorem. All right, so now, once again, we have a right triangle where we're missing one side. So if we want to solve for x, since I have a right triangle, I know I can use Pythagorean theorem. So let's just go ahead and say, okay, well, a is equal to x, b is equal to 2, and our hypotenuse opposite of the 90-degree angle must always be c, so that is equal to 4. We'll substitute in. We have x squared plus 2 squared is equal to 4 squared, and now we're just going to go ahead and solve. So x squared plus 4 is equal to 16. We'll subtract 4 from both sides, and now we get x squared is equal to 12. So when we go to take the square root here, I can't take the square root of 12 like I could with 36 or 25. It's not a perfect square. So to do this, I would have a decimal answer. Maybe this will be 3.4, whatever it may be. But we don't want to give decimal answers, because if we did, we are actually approximating it. And that's what this means with the little squiggly equal sign. So maybe it is 3.4, but we're approximating it. And we don't want to approximate answers. We want to give the definite answers. So these eliminate, and now we have x is equal to plus or minus the square root of 12. We'll get rid of this negative and then just say that x is equal to the square root of 12. But just like in fractions and everything else in math, we never just leave our answers not simplified. So we would then have to see, can I reduce the square root of 12? And since we can rewrite 12 as 4 times 3, and the square root of 4 is 2, I would write that x is equal to 2 times the square root of 3. All right, your teacher next year when you're first learning this might say, go ahead and round your answers to the nearest 10th, but you'll see the more and more you do this, the more and more you leave your answer as a radical. So that way we're given the definite answer, like the exact answer, and not an approximate or rounded answer. So this would then be x is equal to 2 times the square root of 3 as our final answer. So what we were just learning before about simplifying radicals, next year when you get to certain problems, whether you're in geometry or in algebra 2, it is something that you will be expected to do. And that is it for this video.